So today, I will ask you please to keep muted. If you want to ask a question, raise your hand. We will be really pleased to hear your voice if you have questions after the presentation. Today we'll have two amazing guests, and we will start with Dr. Adolfo Chavez. He is a professor and a researcher in Tecnológico de Costa Rica, and he's the coordinator of the Space System Engineering Lab at TEC, and he has a PhD in Space System Engineering. He has been an advocate in the creation of the Costa Rican Space Agency. So he will talk about his work and about the Costa Rican Space Agency so we can all have information about it. And then we'll continue with Dr. Steve.
All right. Thank you very much, Andrea. I don't know if, yeah, I'm able to share my screen now. Perfect. Okay. Wait. Okay. Okay, thank you very much to everybody. It is my pleasure to be here and to be in such honor with such honored guests. I'm going to make a really short talk because Bruce asked me that people would like to know about the proposal for the Costa Rican Space Agency. And it's going to be really short and really justified. In Costa Rica, we had an event that actually marked the life of many people, probably many people who is here connected today, and I include myself among them. For everybody else outside the country, I explained that in Costa Rica in the 80s and 90s, we had an Apollo moment in the sense that seeing a Costa Rican going to space, Dr. Franklin Chang, who was a NASA astronaut and went into space plenty of times, he showed us that a Costa Rican is able to reach for the stars, be able to go to space. And we always say that we want to show that Franklin Chang is not an exception, but it's actually a proof that Costa Ricans can do many things in the sense of first world countries. And what happened is that because of this effect, and this is actually, that's the way I see it, because of this effect, we had a lot of children going for science and technology majors, studying biology, studying space, studying mechanics, electronics, and anything else, and keep dreaming about space. But actually, what happens is that we have a little bit of a problem. Now times, I may say maybe in the last 10 or 15 years, we are so worried only about what surrounded us, what is in our space, and we are so much focused in our problems that all we see is that we are stuck. This is actually a picture of the main road between the airport and the capital. And this is how it looks like almost every single day at 5 p.m. And this is a bridge that became very infamous because of the fact that it had a small problem and it wasn't fixed for, say, 5 or 6 years. This problem coincides with the fact that we propose an organization called CAE and Costa Rica Institute of Technology to create the first satellite of the country. And I always use this example because it was very funny how everybody said, look, we cannot even fix a bridge. How are we going to be able to create a satellite? But we did. It's a small satellite, 10 centimeters by 10 centimeters, really small. But we large amount of people, I would say maybe more than 100 people participated in this project. And also the citizens donated money for this project. And we created the first satellite that went to space. Creating this satellite, we proved that Costa Ricans are able to create a complete space project. By the way, we use the NASA systems engineering method for the project. And by the way, I'm the fat one in this picture. And at the same time, for the first time in many time, the first page of a newspaper was a positive news, showing that Costa Rica was able to go to space. But this was just a really small step in our search to use space technology as a development tool in Costa Rica. What happens in Costa Rica? Costa Rica has a very good education system. We have very good engineers and very good scientists, but we are not creating enough opportunities for these scientists, these engineers, to actually make use of their capabilities. Costa Rica is a very expensive country for only manufacturing, so we cannot focus on attracting manufacturing. But we need to explore new areas that are that have more value, and space is actually one of these areas. Space not only creates more value, but actually helps people dream. It really inspires people to learn mathematics, to learn science, to learn engineering. I always say that we have to make children fall in love for science and technology before people tell them that mathematics is hard. So inspiration can really overcompensate these kind of things. And then for the last 10 years, after Franklin Chan went to space and created his own company, Costa Rica joined UNOSA, the Organization for Pacific Users of Space. We created the first satellite, and we have created many development projects. Right now, we're working in a second satellite and proposing a third satellite, advancing little by little with our own technology. Then, when we finished working on this satellite, we realized that we need to go beyond. For example, how can we take advantage of possible collaboration projects with NASA if we don't have a counterpart in Costa Rica? How can we take advantage of the possibilities that Costa Rica has? For example, Costa Rica has a geographical location that, of course, our guest today could say is very advantageous, because we don't have space countries around, and satellites need to be in contact with other satellites. Then, for example, Costa Rica could focus on having antennas for missions, and with this creating cooperation with other space agencies and private companies. Also, Costa Rica is one of the most biodiverse countries in the world, but also at the same time, because many countries have this amount of biodiversity, we have world-class researchers in biodiversity. So in these exploration projects of going to Mars, living on the moon, taking advantage of this biodiversity and see which products could be used, for example, to live on the moon, could create opportunities in which researchers from NASA, ESA, or other space agencies could come to Costa Rica, because this is the place to work. This is actually the place where we will learn, and this is the place where all the resources are. So we create this advantageous movement of high qualified researchers in both senses. And this is something I tell researchers when I talked about Costa Rica. The idea is not that Costa Ricans don't go to other countries. The problem with developing countries is that for one good researcher that we lost, we don't get a good researcher back. And any country has researchers going from place to place. But the idea is that we create a two-way, process where researchers are working in Costa Rica, working in other countries, and creating this cooperation. Then what we need is to take advantage of this site to impact with science and technology, to cooperate internationally. And actually, Costa Rica is participating in the United Nations, and we need criteria to actually take advantage of the opportunities in UNOSA in the United Nations Organization for Pacific Uses of Space. So that's the reason what we are creating. We propose the project of law of the Costa Rican Space Agency. To talk a little bit about the project of the Costa Rican Space Agency, we are proposing a self-sustainable space agency that will help the public sector with any project to take advantage of the space technology, but at the same time take advantage of the Costa Rican conditions to create alliances with other private and public companies. And with these alliances being self-funded, we are requesting for a small amount of initial investment from the state, but with the idea to have a modern 21st century space agency. Right now at TEC, we are helping on these projects. We finished operating the first satellite, Project Irasu, this year, and we are working with George Washington University in a second satellite project called GWSat. In GWSat, we are creating the control system for the satellite and the environmental system for this satellite. And with this is basically the context that we're working on and the idea of the space agency that right now is in Congress. And we are expecting this may be approved even this year. So if there are any questions, I will be more than glad to help.
Adolfo, thanks a lot for your great explanation. I believe truly on these projects, especially since we are very talented. I've seen Costa Rican students like be bright in external and other countries as researchers. So it will be amazing to have all this technology right here. So I don't know if someone has a question for Professor Adolfo, or we will continue with our guest, Steve.
All right, thank you very much. I tried to do it as short as possible. I hope you get inspired by the idea to actually have a space agency. Me as a kid, I wanted the space agency to exist, and I hope the kids right now will have something to bring on right here.
So congratulations, Adolfo, and your inspiration and your vision is amazing. And it's inspired other countries in Central America too. Now Guatemala has its own satellite, and it's shown what's possible. So yeah, congratulations.
Thank you.
So right now we'll introduce Steve Croft. He's the Breakthrough Listen Project Scientist for the Green Bank Telescope and also lead the pilot programs on the Murchison Wildfield Array. He also heads up industry, community, and press relations and runs the Berkeley SETI accounts on social media. Along with Howard Isaacson, he runs the Berkeley City Internship programs, which is really interesting. And his interests include radio surveys, transistent and variable radio sources, and the relationship between supermassive black holes and their environments. So I don't know if Bruce wants to add something else, and if not, we will welcome you, Steve. Thanks a lot for being here.
Yeah, just again, welcome. From my part, a huge fan. I don't think most people in this conference have seen the movie Contact with Jodie Foster. It's a little bit, I was talking to Andrea about this earlier, and apparently you haven't seen it, which is something on your to-do list. But there's a lot of history in this program, and I'm so incredibly excited to see now that the potential is there. The vision was always there and the commitment, and now there are so many other things that are making it possible. So thank you, Steve, for coming today, and welcome.
Thanks, Bruce. Thanks, Andrea. And thanks, everyone, for the invitation to speak. I'm just going to share my screen. Hopefully you can see the slides. So yeah, thanks very much. You should go see the movie Contact. One of the main characters in that movie, Ellie Arroway, is based on one of the SETI pioneers, Jill Tarter, who was a colleague of ours at the SETI Institute. The SETI Institute is just across the bay from where I am here. I'm in Oakland, California. The SETI Institute is over in Mountain View. And I work at UC Berkeley, University of California, just a few miles north from where I am. Obviously, we're all stuck at home at the moment, but it really means that we have the opportunity to connect in new ways with colleagues around the world, to take opportunities like this. You know, it's as easy to meet with you as it has been to meet with some of our other students that have been working with us this summer. We just finished actually today the final week of our 10-week summer undergraduate program, and it's been really exciting to see people getting involved with SETI research. So I'm going to tell you a little bit of background about what we do, maybe some ways in which you could get involved. The internships, I should say, particularly for sort of folks coming to the US, would require you to have work authorization for the US, so to be a US citizen or permanent resident, or to have a visa already for working in the US, which I'm not sure how many of you that might apply to. But we also are really hoping that people will get inspired about the search. We have a lot of data that's out there, a lot of code that's out there that you can get involved with, and maybe sort of start doing some projects yourselves too. So I'll touch on some of that as part of this talk. So when I was in high school, we really were sort of beginning to understand a little bit more about the universe around us, but I wanted to start with an artist's impression of all of the planets outside of our solar system that were known at the time that I was in high school. Now the situation has changed in the last few years, so we now actually have something to look at if you want to look at planets outside the solar system. And really the sort of field of exoplanets began in the late 1980s. I guess I was still in high school at the time, sort of going into the 1990s, and particularly into the 21st century with missions like the Kepler mission. So this is an artist's impression of the Kepler spacecraft, surrounded by an artist's impression of some of the planets that have been found by Kepler. The art here is by Lynette Cook, who is an artist here in the San Francisco Bay Area. And the reason why we have artists do these visualizations of planets is because taking pictures of planets is really hard. You know, they're little, really pinpricks of light at best surrounding their parent star. Most of them are found indirectly through other methods, looking for their influence on their star, maybe as they pass between us and the host star, or as their gravity pulls the host star backwards and forwards. But we can use the data that we have acquired about these stars to figure out what these planets might look like. And this is a really nice example of science meeting art, right? Where you have an artist working with a scientist. She takes the data from the scientist. She's not just making these things up. It's like, okay, well, we know the size of this planet. It must be a gas giant because of what we know about the physics of planets. We know this one is small and it's probably rocky because we know about its density. We know the distance of planets from stars, and so we can figure out what the temperature might be on the surface. And so we can infer a lot about planets from these indirect measurements. And we now have this sort of whole zoo of planets that have been found. Obviously not all of them quite so close together as they're shown in this picture here, but we're really discovering more about the universe thanks to technology, thanks to engineering, and thanks to the instrumentation that's been developed over the last few years. I think this is one of the most incredible pictures, planet pictures that I have seen. This, of course, is a planet within our own solar system, the planet Saturn. This was taken by the Cassini spacecraft, which flew out beyond Saturn. It flew about 1 billion kilometers into the outer solar system, turned around, pointed back towards Saturn, and captured this image. It's actually a mosaic of a number of different images stitched together of Saturn backlit by the sun. And some people think that this is an artist's impression. Well, no, this is a picture. This is a real photograph from the Cassini spacecraft. And again, taking pictures of planets is hard. This was a big engineering mission. Going there is hard. Flying 1 billion kilometers to take these pictures is hard. But it really also tells us something about our own place in the universe. And that's because actually, although this is a picture of this gas giant planet Saturn, it's also a picture of all of us, of you there in Costa Rica, of me here in Oakland, of all of the people that we share planet Earth with, because there is planet Earth viewed from 1 billion kilometers away, this tiny little pinprick of light viewed in between Saturn's rings there. And I think this picture sort of blows my mind, both from a point of view of how going to space and understanding our place in the universe can really help us understand our situation here on Earth, and particularly how fragile our Earth is. You know, Adolfo was talking about the amazing biodiversity that we have on the planet, and to see that sort of little pale blue dot, as Carl Sagan called it, that one sign of a world with biology that exists there from this distance is really kind of amazing. And so this really gets us thinking, well, are there other inhabited worlds out there? Might we be able to get a picture of another pale blue dot somehow, or maybe not a picture directly, but maybe to infer that life has arisen on some other world? The problem is, to go there is really hard. So I talked about how difficult it is to get to Saturn. To get to the nearest stars, you have to travel distances of 10,000 times further. And so really that's not something that we have the capability to do just yet. But we can go to some of our neighboring planets in the solar system. Some of you have probably seen there's a NASA rover, the Perseverance rover, that's on its way to Mars right now. This is Perseverance's sister rover, Curiosity, or actually I should say a model of it. I guess it's pretty obvious that this picture was not taken on Mars in the top right. Otherwise we'd have succeeded in finding life elsewhere. This is at the Jet Propulsion Lab in California, where they test these robots out. But the Curiosity and Perseverance rovers are pretty similar. Perseverance will have more life-detecting experiments on it, so it can go and scoop up some dirt on Mars and sort of sniff the dirt and figure out if there's signs of biochemistry there, if there's signs of biology, and actually do this direct, the term that we use is in situ sampling, so going to the place and actually sampling there and doing these experiments in place. There are some proposals to send spacecraft to nearby stars. Again, these are very much just in the early planning stages, but there's an initiative called the Breakthrough Starshot program. So I'm with the Breakthrough Listen program at Berkeley, but there's also a program called Breakthrough Starshot, which aims to build a spacecraft on a chip, which will be about a 1 gram spacecraft, to attach it to a solar sail, to build an array of giant laser beams and to fire them at these spacecraft. Actually, you build a bunch of these spacecraft and you launch them up into space with the energy from the solar sail. You release them in space and then accelerate them with the solar sail. Real engineering challenge, very early days in terms of planning this. The idea is these spacecraft would get up to 20% of the speed of light, even before they left the inner solar system. And so they could get to nearby stars like Proxima Centauri just in a few decades. But we're not there yet. This is, you know, it's not quite science fiction, but it's definitely not really sort of settled science and engineering just yet. But it's sort of the dream big idea of what might be coming. But what could we do in the meantime? Well, if we can't go there, then maybe we could use some of these same remote sensing techniques to look at the atmospheres of planets. And so there are missions like the James Webb Space Telescope, which hopefully is going to launch in the next couple of years. It's been delayed quite a bit. But there are missions, or there are observatories like the 30-meter telescope that are planned for construction here on Earth that will just about be able to do these measurements. Maybe it's actually going to be the following generation of telescopes, proposed missions like the LUVOIR spacecraft and some other missions, HabEx, which will be able to do remote sensing for biosignatures in the atmospheres of a handful of nearby planets. So, you know, again, you saw that picture of the Earth from 1 billion kilometers away. Now imagine trying to do that 10,000 or 100,000 times further away, and to separate the light of that planet from its star, it's really hard. But in a handful of cases, we might be able to see examples of simple chemistry that might indicate that there's something else going on there, right? So you see these spectra on the left of this plot here in the infrared, showing the carbon dioxide line that you would expect to see in the atmosphere of Mars and in the atmosphere of Venus. and you look at the atmosphere of Earth and you see there's something different going on. There's water vapor there, there's ozone there, there's maybe other kind of biochemical indicators that you could find. So if we can do that for nearby planets, then we can find potentially these biosignatures. And biosignature, the word just means a sign of biology, right? We're using the sort of chemistry here as an indicator that biology might exist on the surface of these planets. But again, it's a really hard measurement to do. It's one that even in a decade's time or 2 decades time, we'll only be able to do for a very small number of nearby stars. So, okay, we've got 2 methods. We've got in situ sampling and we've got biosignature searches. Is there anything else that we could do? Well, yes, and that's why I'm here. So, like biosignatures, we can imagine that there might be signs of technology that we could pick up, again, across interstellar space. So can we use this as an indicator of complex life, right? Biology could be simple life, it could be complex. You know, looking at the Earth's atmosphere again, you don't know whether that's, you know, algae or, you know, bacteria or trees or people that are sort of manipulating the environment there. But if you see signs of technology, you know that somebody has built something, that there are engineers out there, right? That there are people who are, you know, aliens that are building stuff. And so could we possibly pick up signs of that? Well, we can motivate this search by looking at the technologies that we have here on Earth. And so we have powerful radio transmitters. It might be things like aircraft radar, or even the sort of radar that we use to look for potentially hazardous asteroids that might be coming near the Earth, bouncing radar signals off them. We have powerful lasers that we use, some for astronomical purposes, but some also for communication. Probably actually this conversation that we're having here is as much taking place because of lasers, because of fiber optic cables with lasers on either end, as it is from radio waves. You know, my Wi-Fi, maybe there's other kind of radio communications that are going on that are carrying the data. So people think of radio as being sort of something that you listen to. If you have seen the movie Contact, you'll see Jodie Foster's character is sitting out at the Very Large Array with headphones on, listening for signals. And also our project is called Breakthrough Listen. So maybe you imagine me sitting here in my home office in Oakland listening to the data, and typically we don't do that, right? Because, you know, you can listen to your phone, you can put your phone to your ear and have a phone conversation, but you can also post a picture to Instagram, or, you know, look up a restaurant on Google, or communicate with other devices by sending data over radio waves. And so it's not necessarily something that is represented as sound. It's just there's a lot of signals that are being sent by our devices. You can't really pick up a cell phone on a planet going around another star, but maybe you could pick up one of these more powerful transmitters. And in fact, if you do the math, then you find out that we could do this even for stars that are much more distant potentially than ones where we could have sufficient sensitivity to see biosignatures. And so this is sort of a third leg of the effort here, in situ sampling, biosignatures, and technosignature searches. The first technosignature search was actually done in 1960 by this gentleman, Frank Drake. This was taken a little bit later than 1960, but this is the telescope that Frank used at the Green Bank Observatory. So you're going to hear a little bit more about Green Bank. This is not the telescope that we're using today, but this is the Untitled Telescope, which was there in 1960. And Frank, who just turned 90 years old, earlier this year, lovely guy. If you ever get the chance to interact with Frank, really still very sharp minded and a real pioneer. And Frank put a radio receiver on this telescope that was basically like tuning to a single radio channel, and he looked at 2 nearby stars and he was searching for signals. And actually, as Frank recounts it, early on in the search, he thought he'd found something. They found a signal appear in the data, and they looked a little more closely and they realized it was an airplane. So they picked up some of our own human technology, and really that's the problem with SETI, right? So SETI, I should introduce this term, the search for extraterrestrial intelligence. And as I've mentioned, it's not really a search for intelligence, it's actually a search for technosignatures, it's a search for signs of technology. And Frank found some technology. He just happened to find some technology that was flying overhead in Earth's atmosphere rather than something that was a few light years away. And so this is still the problem that we have today, right? The radio signals that we're looking for. It's motivated by the technology that we have here ourselves, but that's also then the problem of this sort of background noise, and it becomes a search for a needle in a haystack, right? Trying to find this faint signal coming from a distance in this real sea of signals from our devices and from maybe some of these satellites. Hopefully not the satellite that was put up by Costa Rica. I don't think that's the major problem. I think more that Elon Musk is putting up thousands of satellites to give us all internet wherever we go, which is great. But if you're a radio astronomer, maybe that's a little problematic. So when you look up at the night sky and you see all of these stars going, and this is the Milky Way galaxy, so hundreds of billions of stars in the Milky Way galaxy as we look out through the disk of our own galaxy here. If you were to go out tonight and if your skies are clear, and if you were to pick 100 stars, 100 nearby stars, what we've learned, again, since I started high school, what we've learned is that about 20 of those 100 stars have an Earth-like planet at a distance from their star where liquid water could potentially exist on the surface, and we call that the habitable zone, the place where it's habitable. It means it could be inhabited. It's not saying it is inhabited, but maybe life like we know it could exist. Maybe liquid water could exist, and we think liquid water is important for life. And so maybe we can search sort of some of these places. Maybe we can go and look for habitable zone exoplanets, look for ones that are in the right place with the right conditions, and then do our technosignature search there, even if the biosignature searches aren't powerful enough to find the signs of biology. And it turns out because 20% of stars have Earth-like planets, we can actually just go and look at all of the stars. Why do we need to pre-select the stars that we're going to look at when we could just cast a wide net, look at lots of stars of different kinds, and see if we pick anything up? This is another incredible image. This is taken by the Hubble Space Telescope. It's the Hubble Ultra Deep Field. It's the one of the longest exposure pictures that's been taken by Hubble. I think this is basically about 11 days of shutter open time on the Hubble Space Telescope. And what you're seeing here is a region of the sky that is about the size of a grain of sand held at arm's length. So imagine holding up a grain of sand to the sky, and there's this tiny little region of the sky. I don't know whether you can see my cursor here as I'm pointing. There's a star that is close to the center of the image here with these spikes coming out from it. That's why you can tell it's a star. It's a little point of light. There's another star down at the bottom here. The one that is near the center is about 10,000 times too faint for you to see with a naked eye, and that's one of the brightest stars in the picture. So actually, this region of the sky that is the size of a grain of sand at arm's length, if you looked at it with your naked eye, would look completely blank. You wouldn't see any of this. You wouldn't see any of these stars, and you certainly wouldn't see any of these galaxies, and that's what these other things are. There's some nearby galaxies. There's some galaxies that are further away. There's some very distant and very small galaxies. There's about 10,000 galaxies in this image, again, in this very small region of the sky. And then if you imagine extending that view over the whole sky, multiplying that little field by the whole sky, we realize that there are hundreds of billions of galaxies that are out there just in the observable universe. And so, hundreds of billions of stars in our galaxy, hundreds of billions of galaxies, maybe something like 10 to the power 22 potentially habitable planets out there, maybe something more, a little bit more, a little bit less, but many, many places where life could potentially arise. And so where is everybody? Why have we not seen any signs of life elsewhere? And this was sort of the profound question that this physicist, Enrico Fermi, had come up with, sometimes expressed as Fermi's paradox. If life is common, why have we not detected it yet? And there's a number of answers, possible answers to that. Part of the reason maybe that we really are alone in the universe, that we are the only inhabited planet. Part of it may be that other inhabited worlds are very far away, or that other civilizations don't choose to broadcast evidence that they're there, or maybe they're deliberately avoiding us, or maybe they've sort of blown themselves up in some kind of like interstellar warfare. I don't know. There's a number of solutions that have been proposed. But really, we can sort of sit around and talk about this, or we can actually go out and do an experiment. And that's what we're doing. We're going out to do the experiment to see if we can detect this. And then we can maybe put some numbers on this and find out if they're not out there, then we can put some limits on how many transmitters there might be. So in 2015, thanks to the sponsorship of the Breakthrough Initiatives, and in particular, Yuri Milner, who is an internet investor here in California. In 2015, the Breakthrough Listen project was announced, and it's $100 million over 10 years to really revitalize the search for extraterrestrial intelligence, to provide new instrumentation, to provide time on telescopes around the world, and to provide the staff, the scientific staff, to carry out the project. And so I'm a part of this project. I'm not the director of the project as a whole. As you heard in the introduction, I run our program on the Meerkat Telescope, and I also run our undergraduate program with the group. But my boss, the director of the Berkeley SETI Research Center, Andrew Simeon, is the principal investigator for Breakthrough Listen. And when this program was launched, Andrew called me up. We were getting a lot of media requests that he couldn't handle all himself. So he said, I want you to go talk to Fox News. And I was like, okay, I guess somebody has to. So I went and talked to Fox News, and this was the screen grab, and they had some sort of interesting other video showing of astronauts on the space station, and sort of somebody had Googled, space videos, and these were playing in the background, and they were asking me, what might the aliens look like? And I guess it was fun, but it's kind of a strange interview. So it's nice to speak to audiences that have a little bit more, technical background, a little bit more scientific background, and interest in the area. And that's why it's great to be here today and to sort of get a little bit more in depth into some of this. So here's the Meerkat Telescope. The Meerkat Telescope was the first big radio telescope to join the Breakthrough Listen project. The photograph that you see here, this is on the left is our chief engineer, Dave McMahon. He designed and built the back-end instrument that we have at Meerkat. And then you see the dish here. This is the size of 2 football fields. It's about 100 meters across. It's about 7,000 tons of metal, taller than the Statue of Liberty. You can just about make out, maybe on your screen here, there's some people down at the bottom here and some ropes. When I took this photograph, the people had just rappelled down from under the side of the dish. They'd been painting the dish during the day, and they just finished for the day and rappelled down from the dish here, and we're getting back into their vehicles. So this thing is huge. If you go to our YouTube channel, we filmed a 360 virtual reality tour of the Meerkat Telescope. You can either watch this on your computer and click and drag and look around as we go up the stairs and up the elevator, walk across this platform, go up another diagonal elevator to the top and look down on the surface of the dish. It's really kind of fun to see that. If you have a VR headset, you can get sort of some pretty cheap VR headsets like Google Cardboard that you slide your phone into, and then you can kind of pan your head around and look as you're taking this ride. And I encourage you to go check that out. It's kind of fun. We're also working with the Parkes Telescope in Australia. Another great movie recommendation is a movie called The Dish, which is about some Australians who helped NASA out with getting the signal back from the Apollo 11 moon landing. It's a really fun movie about sort of, NASA and their kind of like buttoned up sort of, engineering culture. And then there's these Australians who are like, right, we're going to step in and sort of just kind of fix things and do things kind of on a budget. And they managed to pull it off and to get the signal back from Apollo and to assist with the Apollo landing. So that's definitely a fun one. And again, we have instrumentation there as part of the Breakthrough Listen program. Here is, this is just 50% of the equipment that we have at Green Bank. So this is the back-end instrument. There's another sort of copy of this that's in another room, so we don't get the whole picture of this at once. And these are computer servers that are just all racked up. They're basically just very powerful computers, but sort of off-the-shelf computers, basically, that you could buy for a lot of money. If you have a few $100,000 burning a hole in your pocket, then you can go and buy some equipment like this. But it's really a bunch of hard drives, a bunch of storage, and then there's a bunch of memory on there, and a bunch of graphics processing units. So these are GPUs like you might have if you're a video game enthusiast in your computer. We use these for doing the data crunching, basically for taking the data from the telescopes. And there's some sort of technical numbers on the right here that sort of tell you what we're capable of there. Some of them might not mean very much to you, but 12 gigahertz of bandwidth. So this basically means, if you think of Frank's original experiment, not exactly sure what the range of frequencies that he had was there, but it was a single channel I told you that he could tune. We actually have finer resolution, so we get about 3 hertz of frequency resolution. That's a very narrow region of the radio spectrum, and if it helps to put it in context, right? If you listen to FM radio is frequencies of sort of 80 megahertz up to about 105, 110 megahertz, something like that. We're typically doing our experiments a factor 10 to 100 higher in frequency. So we're looking at 1 gigahertz up to about 12 gigahertz. And we're looking at all of that. We can potentially look at all of that at once with a resolution, with a channel, a frequency channel of 3 hertz wide. And what that basically means, you know, again, sort of simplifying a little bit, is we're listening to 1 billion radio stations at a time, or several billion radio stations at a time, compared to what Frank was doing with that single channel in his experiments in 1960. We have 8 petabytes of storage. Probably the laptop in your hard drive is a terabyte. So this is sort of 8,000 laptop hard drives, something like that. They're in the instrument. I don't know how to sort of put 500 teraflops of computing into context, but it's a lot. And each of these boxes right here, so this is what we call a compute node. Each of these is writing 750 megabytes of data to disk every second. Multiply that by 64 of these boxes, observing 5 hours a day. And that gives us hundreds of terabytes per day. So filling up your laptop hundreds of times every day of raw data since the beginning of 2016. And we can't possibly keep all of that data, so we have to do some analysis on it. And actually we archive a smaller fraction of that, so about 2% of the data volume. We average it down, and that's what we save. But these are the data that we're using to do our searches that we're looking through for these technosignatures. Problem is, if you look at the frequency spectrum, and so this is sort of, if you chopped all of these little strips out and joined them together, then you would get kind of the frequency allocations here in the US from 3 kilohertz up to 300 gigahertz. And again, you can probably sort of dig around here and find FM radio is going to be somewhere, can't quite see it, I need new glasses obviously, but it's sort of somewhere in the middle here, around 100 megahertz or so. So we're typically a little bit further up. There's some bits here that are, oops, I guess I have it on this particular slide. Get back. There's some parts of the spectrum that are reserved for radio astronomy. And again, if you have an experiment like Frank Drake's original experiment, that's fine. You stick to the radio astronomy band, and you're just like, okay, I'm just going to look here at this little bit. But when you have an instrument that can look at billions of channels, you're going to pick up a whole bunch of junk as well. You're going to see satellites, you're going to see cell phones, you're going to see Wi-Fi, you're going to see garage door openers and microwave ovens and all sorts of other things. And that's a problem, even when you're in the middle of the National Radio Quiet Zone in Green Bank, West Virginia. So the federal government has said, we're going to have this area actually largely to protect the astronomy observations at Green Bank, where there's much tighter regulations about transmitters. But it still can't get you away. Maybe it can get you away from some of this. And there are regulations on Wi-Fi, for example. There's a great article, if you go and look up, about Green Bank, West Virginia in the New York Times about the town where there's no Wi-Fi. And people think, how can they live with no Wi-Fi? This sounds terrible. But there's a town there where, you know, it's just, they still have internet, but it's, you have to plug in to get the internet. But it doesn't get you away from satellites going overhead and other you know, and people that haven't turned off their cell phones and have ignored the signs near the Green Bank Telescope. So how can we get past this? How can we get around the fact that, you know, again, Frank's first experiment found an airplane. How can we not have the same problem? Well, if you think of a microphone, a directional microphone that points in a particular direction, and if you were trying to pick somebody out of a crowd with a microphone, you can imagine pointing the microphone at them and putting your headphones on and listening, and you're hearing all the noise from the crowd, a crowded room maybe, or a crowd outside. And then you could move the microphone a little bit, and maybe you're still picking up the crowd with the microphone, but maybe now you're not getting the signal from the person that you were pointed at that you're interested in. And so you move that back towards that person. And now if you compare the signals between when you're pointed at the person and pointed away from the person, comparing this, on target and off target, on target and off target, and pointed at you and pointed away from you. If I compare these signals, the crowd noise is going to sound pretty similar in both of those positions, but looking at the difference between those signals, I can maybe see the signal that's uniquely coming from the direction that I'm pointed in, and maybe that's you, the person that I'm interested in listening to. So we can do the same thing with GBT. So there's sort of a photograph there on the left and then a schematic on the right, which really is a little bit like sort of sensitivity plots that you might have seen for microphones, where it's like, we're really sensitive in this direction and we're not so sensitive in the other directions. So we point the telescope at a star and then away from the star and then back at the star and away from the star, and we compare the signals as we're pointed on and off target. And we wouldn't expect somebody with a cell phone or Wi-Fi device, or even a satellite going overhead, which is going to be moving, either moving across the sky, or even if it's a geosynchronous satellite, it's going to be moving relative to the stars because the stars are moving across the sky as we track them. So we can do this on-off observation and compare what we see in those different directions. So this is what we call a waterfall plot. This is some data that came from just one of those computers that you saw at Green Bank. Again, there's 64 of these, and you're seeing a small region of the spectrum, or relatively small, 187.5 megahertz across, ranging from about 2300 megahertz. So again, sort of factor of 20 higher than FM radio or so, up to about 2500 or so on the right, so frequency on the x-axis, and then time on the y-axis. And this is measured in seconds, sort of in strange units, but this is about 5 minutes of time here. And then the colors in the middle here are showing the power of the signal that's coming in at that particular frequency at that particular time. And you see a bunch of vertical lines here. That's actually just part of how we split the spectrum up into its channels. But we can basically pick up any signals that are in this range that are particularly powerful over this particular length of time. And if you look closely, again, if you ignore these sort of vertical stripes, you can see there's some little kind of squiggles here, maybe a squiggle here, maybe some other kind of stuff that's going on over here. And if you just had this one data set, you might think, well, is this it? Is this ET? Did we pick up the signal that we're looking for here? Well, no, you've done your on observation. Now you have to do an off observation. So now we're going to go and point the telescope elsewhere. We're going to get some more data, another 5 minutes across the same range of frequency. We still have some kind of bit of a signal here, maybe now a bit of a signal here. Let's do this a few more times. So we're going on the star, off the star on the left, then on the star again in the middle at the top, off the star again at the bottom, on the star at the top, and off the star at the bottom. So now we've done 30 minutes of observing on, off, on, off, on, off. And all we have to do to find ET or to find a techno signature is to look for things that are in the top row that are not in the bottom row. So things that appear only when we're pointed at the star and that don't appear when we're not pointed at the star. And you can sort of do this by eye, right? You can look at the data. We don't do this all by eye because there's a lot of data, but you can look at the data and say, well, let's take those two right-hand panels and compare them. So we see the signal here. Well, it's there when we're pointed at the star, and it's still there when we're pointed off the star. These big sort of vertical stripes in the middle, and also some of these kind of squiggly signals here that are off to the side, which seem to sort of come and go, and they're seen in some of these other panels here as well. So I don't think any of these things are techno-signatures, right? None of them seem to be uniquely here, always here in the top row and not in the bottom row. And you look at this signal on the right, 2400 megahertz, this sort of bright signal. I know about 2400 megahertz. Well, 2.4 gigahertz, right? That's a frequency that maybe You know, if you've ever looked at a Wi-Fi router and connect to a Wi-Fi router, right? They're doing their communications at 2.4 gigahertz typically, or maybe 5 gigahertz. There's also Bluetooth and some cell phone communications that use these frequency bands. So this signal is probably Wi-Fi. It's probably somebody standing near the telescope who has ignored the signs that say, please turn off your Wi-Fi, and they're trying to get a Wi-Fi signal in Green Bank, West Virginia, and the telescope is picking it up, even when it's not pointed at them, because their cell phone is such a bright source of radio waves. Even when it's close by, the telescope doesn't need to be pointed at them to pick it up. But fortunately, we can exclude this as being a technosignature because of the technique that we use to compare the on and off observations. Another thing that we can do, if you've heard the siren of an ambulance as it goes past, you'll hear the change in pitch of the siren as the ambulance is going past, as the frequency is changing, as it is. So there's a frequency shift, a Doppler shift, we call it, a change in velocity, but there's also a Doppler drift, and that sound, right, as the frequency is changing, is because there's an acceleration, not just a velocity, but there's an acceleration, a relative change in velocity as the ambulance passes. And so somebody with a cell phone standing by the telescope, their cell phone is always going to be broadcasting at the same frequency, around 2400 megahertz. It's not going to be changing in frequency with time. But if the telescope was moving fast relative to the cell phone, or if the cell phone equivalently was moving fast relative to the telescope, you might tend to see a change in frequency of the signal with time. And so that's another way that we can use this to say, well, this is not something that's coming from nearby the telescope. We can throw the signal out because it looks like a vertical line in the data here in one of these data sets. It's constant in frequency with time. Whereas if the signal was diagonal in one of these plots, it's changing in frequency with time. It's either something, the transmitter is changing in frequency, or the transmitter is moving relative to the telescope. Maybe it's moving because it's on a planet that's rotating, or because we're on a planet that's rotating. And so here's a graphic that sort of illustrates this, and this idea of Doppler drifts, right? You've got planets going around stars, you've got telescopes that are on a rotating planet, you've got signals that are coming in, and the frequencies of those are going to be changing with time, maybe in a way that we can use to give us a bit more likelihood that a signal is coming from somewhere else other than nearby to the telescope. So we can do this again, do these on-off observations. Here are 8 different stars that we pointed at. And here we're doing these on-off observations. We're just stacking up the 6 observations in each of these panels here. So we've got 5 minutes on, 5 minutes off, 5 minutes on, 5 minutes off, 5 minutes on, 5 minutes off, for 8 different targets. And the goal here now is to find things that are in rows 1, 3, and 5, and are not in rows 2, 4, and 6 in these plots. So that's the same as this on-off comparison. So can we see things that are drifting in frequency? Well, here's something, I don't know whether you're really seeing my cursor here, but there's something that's drifting in frequency over time, that's coming and going as the telescope is on and off. And that's what we would expect an ET signal to do. That's what we would expect a technosignature signal to do. So have we found, 8 advanced civilizations? Is that what I'm showing you here? No, you'd have read about this in the news if we found 8 alien civilizations. It actually turns out that there are signals, even after we sort of do these filters, that still can mimic the signals that we're looking for, that still make it through these cuts, but a lot fewer of them. So when we can get rid of a lot of the background noise, and it gets down to just a handful of cases that we can then investigate more carefully. And actually, I don't know whether you can make out the frequency on the bottom here, but most of these are around a frequency of 1380 megahertz. And unless that's a particular frequency that ET likes to pick, even if there's 8 of them in different places and they really like 1380 megahertz, that should be ringing an alarm bell. And you're thinking, okay, maybe there's some human technology that happens to transmit around 1380 megahertz and sort of switches on and off occasionally, maybe with a cycle of a few minutes where it tends to be turning on and off, and then we're picking it up and not, and it's sort of fooling us in this case. And we do think, in fact, I think these are sort of some satellite communication band. I forget off the top of my head what these are, but we sort of threw these out. These are not great candidates after we investigated them a little more. So in the interest of time, I guess I'll skip over this, but we really want to be able to sort of draw boxes around these signals and maybe sort of classify them as being weird or not weird. And we think machine learning can really help with this. We've had some interns working with us this summer who've been doing machine learning analysis in the same way as a self-driving car can draw boxes around a pedestrian or you know, a lamp post or whatever. We've had some early, and this is I hand drew these boxes, but we've had, like this summer, we've been sort of making this a reality where the interns have software now that can actually draw boxes around some of these. And so, you know, if ET was transmitting again here, if you imagine they put some signal in that looked really weird, that's only in the on observations, that's only in the top row, we'd like to be able to draw a box around that as well and say that looks nothing like the other signals. It looks really strange, and it's only there when we're pointed in that particular direction. So let's go follow that up. I'm going to skip that. So it does look a little bit initially like we're looking, as I say, for a needle in a haystack. But if we can cut down the size of the haystack and just throw away a lot of the hay, then maybe finding that needle is a little simpler. I mentioned a little bit about sort of using these tools like machine learning. So one of the things that the sponsor, Yuri Milner, said at the launch of Breakthrough Listen is he wanted to bring a Silicon Valley approach to the search for extraterrestrial intelligence. So using tools that companies like Google and Facebook and other companies use for looking through big data sets to find interesting things. And you know, if you type ET into Google, you get a bunch of pictures of ET. Google's got to be pretty good at this. You even get, I like this one down in the bottom right, you get ET dressed as Mr. T. So, you know, Google's pretty good at sort of figuring out like these images belong together. And we hope that we can use some of these techniques to find out which kinds of signals that we pick up belong together and say, okay, these things are Wi-Fi, these things are Bluetooth, these things are, you know, weather satellites or cell phones or whatever, and to throw those away, to throw the haystack away, and then to get the few interesting signals that remain. I'm going to skip over all of this because this is, don't really have time. This plot here, so I said, you know, we don't have any signs of extraterrestrial intelligence. Well, here is one sign of extraterrestrial intelligence. I'm kind of cheating a little bit here. This is actually the Voyager 1 spacecraft. So it's extraterrestrial because it's way out in the outer solar system, but it's human. We built this thing. Humans built it, launched it out there. And the Voyager 1 spacecraft is currently way further than the Cassini spacecraft that I talked about earlier. It's currently way further out than Saturn. It's about 20 billion kilometers from Earth right now. And this is a real scan. This is real data that you're seeing here from the Green Bank telescope when we pointed the telescope at Voyager 1 and picked up the signal, the transmission from Voyager 1. In the middle, the spike that you see in the middle here is just the sort of the carrier signal. It's Voyager saying, hey, I'm here, you know, here's a bright thing for you to lock onto. And then on either side there, you see the data signal, and it's sending down data at a really low rate. I think it's like a few hundred bits a second, so it's way slower than your home internet, but it's way out in the outer solar system. The transmitter is 20 watts. So the transmitter is about the same power as the light in your refrigerator. And we can pick it up from 20 billion kilometers away with the Green Bank telescope, which I think is really amazing. And actually, one of the students, actually a teacher, a high school teacher who we were working with this summer was doing a project with me where we took some new data on Voyager 1. And we actually pretended that it was one of our regular targets. So we did these on-off observations of Voyager 1, and then we fed it through our regular analysis pipeline and asked the pipeline to only show us things, basically, again, if you think of those plots, only show us things that appear in that top row when we're on target, only show us things that are drifting in frequency with time. And the algorithm kind of worked for a little bit and found a bunch of things and then threw out a bunch of things that are in this haystack, basically. And it returned two signals. It said, I found two things. One of the things that it had found was the carrier signal in the middle of Voyager 1. One of the things that it had found was one of the data signals, and it just missed the other data signal because we'd set the threshold to be a little bit too high to see that other data signal, but I have no doubt that we would have picked it up. And those are the only things that it found in this search. It's like, great, it works. We found this techno signature, right? The technique works. Maybe this would also work even for things that are thousands of times further away, which would mean they would have to be millions of times more powerful than that 20-watt transmitter, but it's not out of the question. You can go, probably easier to just kind of Google Voyager 1 tutorial, Voyager 1 breakthrough listen. You can actually go and get the data yourself. You can load it up with some software that we've made available. You can zoom in and find those signals. We're going to be putting another tutorial out pretty soon that is based on the work that this teacher, Ilan, did with me this summer, where you can actually run the search end to end and look for the signal in the data yourself using the software. If you have a little bit of Python programming, then you can play around with that. There's some more sort of tutorial stuff that I've got out there on the web. How do we find ET? Well, first of all, you've got to get some data, and then you've got to read the data in, and you've got to work through the analysis tools. But I have a lot of kind of curriculum stuff that's there. I have some more videos that we did for our interns this summer where you can go and watch several hours now of video material that sort of take you through the background that you need to know to do these kind of searches. I'm going to skip over this again. Sorry, I've sort of gone a little long here, but there are other searches that we do with optical telescopes, looking for lasers, as I mentioned before, looking for bright flashes. I'm not going to go through that. I'm not going to go through that. And then I mentioned there's public data, so you can go, there's now about 2 petabytes of data. So, again, if you've got a 1 terabyte hard drive, you could fill it 2,000 times just with data that we've made available to the public, and it's going to take you a while to download that. So start small and play around with a little bit of it. And then I wanted to end with this picture that I took. There's some beautiful scenery around here as well. I'm not sure how this compares to the Costa Rican rainforest. I've heard it's really stunning. This is not really a rainforest, but this is redwood trees that are about maybe 5 kilometers from my house here. And we take our dog for walks up there in the redwoods. And there are signs up there that say, be careful, watch for mountain lions or pumas that are up there in the forest. And if you're walking the dog, particularly if you have a small child, you've got to watch out for them. You don't want to be attacked by a big cat. But I don't see any pumas in this picture. So there must be no pumas right in the forest, since I'm not seeing any right here. Well, no, that's not how this works, right? It's just, you need to look a little harder. And I think for me, the answer to the Fermi paradox is just that we probably haven't looked hard enough yet. And there may be a puma right behind one of those trees right there. You just have to sort of go and poke your head around the corner, or make sure that you're using the right techniques, or that you're coming out at the time when the pumas are active, or you're looking for signs that they were there. Maybe they scratched on a tree or something. And so I think if we do a scientific experiment, and particularly if we do a scientific experiment where we're taking a lot of data and making the data available to the public to examine, people with smart ideas, people who have some machine learning experience, who have some data science experience, or maybe you can develop that using the data, then we really are closer now to the answer to this question, are we alone in the universe, than we were before we started. So as some folks said at the beginning of the dawn of SETI, these folks, Ciccone and Morrison, the probability of success is difficult to estimate, but if we never search, then the chance of success is 0. Thanks very much.
Thanks so much for your presentation. It was truly great. I am a true believer that we're not alone in the universe. I mean, we're a rare casualty. Humans, we are rare, but we can be that rare, right? The universe is too big. So yeah, it's really cool to see that things like you're doing things like this. And now I think I have a lot of questions, of course, but I'm pretty sure a lot of people have questions. So I want to open this space for everyone to ask whatever questions they might come up with. So I don't know if you would like to write it, or you would like to open your mic to do it. So we have one from Mauricio, and it's, how do you select the regions in the sky to survey?
Yeah, good question. So I mentioned earlier the experiment again that Frank Drake did in 1960, where he looked at 2 stars, and he was very careful to select those stars. And again, 1960, before we knew that there were planets anywhere outside the solar system. So he picked 2 stars similar to the sun that were relatively close to Earth. If you had the ability to only look at a handful of stars, then you should go and look at the stars that have been searched by Kepler or by the TESS spacecraft or by other planet hunting missions, and you should look at ones that we know have small rocky planets at the right distance of the star for water to exist, these habitable zone planets. But if you have 20% of the time on the Green Bank telescope and you have an instrument that can, digitize 12 gigahertz of bandwidth and, you want to do a more comprehensive search, then you can look at more targets. And in fact, that's what we do with Green Bank. We're looking at basically every star that we know that's within about 20 light years of Earth. We're looking at a sample of stars, so we're picking a representative sample of stars that are within 200 light years of Earth. And then we're looking at some other stars, including some stars from the TESS catalog. We're looking at some weird stars. We're looking at some other galaxies, just in case there's really powerful transmitters that are out there in other galaxies. We've even looked at a couple of things within our solar system. So there was this Interstellar Asteroid, Oumuamua, which you may have heard about. It came through the solar system. Some people said it looked like a spacecraft. It's this kind of big, long, elongated thing. You might think that's crazy. One of the people that said it looks like a spacecraft is the chair of the astronomy department at Harvard University. And so if he says maybe it could be a spacecraft, then maybe we should go look at it. So we looked at it. We didn't find anything. But so we can do a broader range of searches. And then what we're actually going to be doing, I didn't mention this, but we're starting a project with the telescope in South Africa called the Meerkat Telescope, which is going to be able to do surveys of 1 million stars compared to about 1,000 or so that we've done to date. And so that's going to really help us to expand the search to a lot more places.
Great. We have another question from Matus, and he says, let's assume SETI receives ET signal. What's the line of action? What does public get access to it too?
Yeah, great question. So there are procedures in place. They're called post-detection protocols. And so these are sort of internationally agreed upon plans, basically, of what we should do. And this comes under the authority of a body called the International Academy of Astronautics. And there is a SETI permanent committee. It's about, I think now about 60 scientists and engineers. I'm one of the people on this committee that has basically agreed this is what we should do. And it amounts to, first of all, check that it's correct. You don't want to go out there and announce something that you're not sure is really a techno-signature. And one thing that you should do is have somebody from an independent group, an independent research group and an independent telescope, right? If I say, I see a signal coming from this star, well, somebody else should look at that star and we should compare and make sure we see the same thing. And then once we're sure, basically there are a couple of things we tell I think it's like, it goes to the Director General of the UN and it goes to, the relevant sort of authorities basically as broadly as possible. So you don't just phone your government up and tell them, hey, we found aliens, because that might not end well. But I think in the modern era as well, probably what we would do is we would put the data out there, on Google Cloud. We would announce it on Twitter with a link and we'd say, hey, everybody, have a look at this. We think we found something really interesting. We want everybody to go and look at this and check it and see if we've done, our analysis correctly, and make this be a thing for the whole world, basically, to help us confirm. Now, if it's one of those things that looks like the kind of alien head cartoon that I drew in some of the data, maybe it'll be more obvious than others, but still, like, my first suspicion if we found that would be like one of our students has kind of snuck in and like manipulated the data somehow. And so that's why it's also important to get somebody else to confirm it. You don't want to go out there and announce something and then have to retract it. But I guess the short answer is we want to announce it as broadly as possible. And that's one of the reasons why we think it's really important for the search to be public, for as much of the data to be public, and the software and the analysis that we're doing to be public as well.
Thank you very much. We have a question from Roberto Inés. What if life flourished in the universe at the same time, and intelligent life have been transmitting like us, radio and TV, just for the last 50 to 100 years?
Right. So I mentioned Frank Drake. I know his name keeps on coming up, but one of the other things that Frank did in 1961 at a meeting at Green Bank, and again, Green Bank keeps coming up here, Frank came up with an equation called the Drake equation, and I didn't get into that here, but the Drake equation basically, and I won't have time to get into it in detail, but it helps us estimate how many other technological civilizations might be out there. And we multiply a bunch of numbers together, some of which are, you know, how many Earth-like planets are there, what fraction of Earth-like planets end up having life on them, what fraction of life ends up developing technology, and so on. You can go and look up the Drake equation. There's some sort of interactive websites where you can go around and play around with the numbers and sort of figure out your estimates. One of the things to Roberto's question that's really important is the lifetime of the civilization in the Drake equation. And actually, you know, if you play around with the numbers a little bit, particularly if you're an optimist and you think that we know, okay, now we know, and Frank didn't know this in 1961, Earth-like planets are everywhere, right? 1 in 5 stars. And then if you assume that life is inevitable, intelligence is inevitable, you know, communication is inevitable, that in all of these cases, there's a 100% chance that life gets started and develops technology, which I'm not saying that that's true, but if you assume that, then you find that the number of civilizations that you expect in the galaxy now is equal to the lifetime of that civilization in years. And so again, you know, to this question here, if it's 50 to 100 years, that would imply, again, in the optimistic sense that it's all inevitable, that there are 50 to 100 signals out there for us to find. And if the lifetime of a civilization is 10,000 years, you'd expect 10,000 signals. If it's 1,000,000 years, you'd expect 1,000,000 signals. Again, if you're an optimist about the chances for life, if you're a pessimist and you say only on 1% of planets where life could arise, does it actually happen? Only 1% of life develops intelligence. Only 1 in 1,000 intelligent species are using radio transmitters. If you're pessimistic, then this sort of goes out the window. But this is another nice thing that you can do with the SETI experiment by going out and measuring, right? You can say, well, are the measurements that I've done consistent with there being 1,000,000 signals out there, or 1,000,000,000 signals, or whatever? You can put a limit on that, and you can make that limit tighter and tighter. And you can say, well, then I think probably what we're measuring here is that there typically aren't, you know, a whole lot of civilizations that are very long-lived. And maybe that tells you something about civilizations in general. And again, there's a sort of a mind-bending quote from these guys, Cocconi and Morrison, that SETI is the archaeology of the future. What does that mean? Well, it tells us what happens to civilizations on average. And so it gives us an idea of what might happen to a civilization like ours. Are civilizations common, or are they short-lived, or are they very rare? And we have a chance of actually measuring that.
Archaeology of the future.
Thank you. So we have Bernarda's question, and I want to add something on this because I know it will be very helpful. So engineering students with a passion for space and the search for extraterrestrial life from another country, not a citizen of the US, how could you participate in internships? When will open? So I want to add something before. There's this J1, because I know you told US citizens, there's this visa called J1, and Costa Rican students can go to the US and make internships for up to 1 year. So that's an option. So yeah.
Yes, so we have not typically just sponsored visas for people who have not already been working, you know, on data analysis in some way. So we do have people that have come for jobs with us, you know, either on a J1 or potentially on H1Bs or other visas. You know, we've hired people from around the world, some of whom have come to live in the Bay Area. we're also collaborating with people at other places. So we have some colleagues in South Africa and in Australia, where they're working in their home countries, but working for the project. In terms of the internships, so we do have our internship program, and I did sort of, I flashed up there on the screen at the end about applications for our main internship program. I would say, unfortunately, don't apply for that if you don't already have a work authorization. We can't typically work to sponsor applicants to that program for visas, particularly given the difficulty of doing that on a timescale for a 10-week summer program, the difficulty and the expense really of doing it for a 10-week summer program. So for now, those positions are limited to folks within the US already. I mean, maybe some of them are on visas like an F1 visa at another university. We've had a couple of F1 students participate this summer who are not typically eligible for National Science Foundation funded internships, but we do have some money that we can use if they have a visa already to work with us. But what I would say, I mean, a couple things. I just got done with our 10-week summer internship, and it was intense. And I'm sweating a little bit now. Maybe you can tell. It's actually just because I'm in a house that doesn't have air conditioning, and it's one of the hottest days of the year here. Typically doesn't get this warm. But I also really feel like, wow, okay, right, we're done with our summer internships. Like, I'm going to be able to get back to do a little bit more of my own research, and some of my colleagues are going to be able to kind of get back. I mean, it was super fun this summer working with these students. We had a really great time. They did some great stuff, but it was really pretty intensive with 15 students working with us this summer. And there are a lot more people who are interested in working with us and who are interested in getting involved than we can support with the staffing on our end. So while I'd love to say, to all of you, like, let's work together, or, send me an email and, we'll collaborate. I think an easier path is, again, as I mentioned, that we have some public resources that are out there. We have public data. We have tutorials that are out there. And now, and this is a benefit of the fact that we've been online for this summer program rather than doing it in person, all of the lectures that our interns had in the first week of their summer program, and then additional lectures that they had throughout the 10 weeks that they were working with us, are now up on YouTube. And so you can go and watch those lectures and do the same kind of curriculum and learn about the software and learn about the data as you could if you came to work with us in Berkeley. And so what I would say is, if you're interested, work through some of that stuff, have a play around with the data, at least get to the stage where you can work through some of the tutorials. And particularly if you can think about sort of directions to take this, that take it in a different direction. If you're already kind of up to speed, and I would say this is sort of general advice that I would give any of you, for applying for internships in general, and it may not be just reaching out to me, but if there are professors at other universities in the US, or, elsewhere in the world, or even in Costa Rica, that you'd like to work with, sending them an email that's like, hey, professor, have you got any research positions? Maybe some of them will, and you can try that. But I think if you reach out to them and say, hey, professor, I read a couple of your papers, I watched your online video lectures, I downloaded some of your data, I have an idea, I've been playing around with this. You're much more likely to break through. I didn't mean to use that word, but sort of to get somebody's attention, basically, if you can show that you have interest and are already sort of taking the first steps. So, maybe this will change in the next few years. Maybe we'll be able to sort of come up with something that is open to applicants worldwide, or maybe we have some partnership with folks in Costa Rica where they could be mentoring students locally, and you could be working with them and collaborating with us. We've done some similar stuff like that in Ireland with a couple of students who worked with a telescope over there, but they had already their university in there to support locally. But there's ways that I hope that this will change. And really, as I've said, sort of SETI, I think particularly, is an endeavor for us as a global species, right? It would be great to work together on this. And so I guess I just, I apologize that, right now, just given the small team that we have in Berkeley, I can't sort of respond to everybody in detail individually and mentor everybody in the way that I wish that I could, or open up the internships to everybody. But I hope there's enough here that if you're interested, you can still find something where you can get a little bit hands-on and then maybe kind of get into the field and sort of work with us down the line. I hope that's an okay answer.
Well, thanks a lot for it. We have a lot of more questions. For example, we have Isaac's question, and it's, how about flying saucers, UFOs? Are these verified as extraterrestrial beings, or are stories about them just myths?
Good question. I mean, I think this is sort of outside of the investigations that we're doing with Breakthrough Listen. I think it's very important always to kind of take a scientific approach. And I wouldn't say that these investigations are sort of outside of the possibility to be examined scientifically. But everything that I've seen in this area is sort of not super convincing, right? There's a lot of people that make claims about having seen pretty wild and outrageous things, right? If you go and look on the internet and you find sort of conspiracy theories, or, what do people believe, or, what strange videos are out there and this kind of thing. There's a lot of stuff that's out there, and you could spend your life kind of going down a rabbit hole sort of investigating some of these things. And I think, I'm not really going to take a position on UFOs. I mean, you've maybe seen sort of some of this stuff from like the US military, where they have, cameras that have been tracking objects that look like they're behaving strangely. I'm a little bit suspicious that ET would travel 1 trillion kilometers. We already looked at how hard it is to get out into the outer solar system, right? How hard it is to get between stars. Like, I don't think they would come here and be doing stunts somewhere off in the Pacific, and instead of just landing, in the middle of, capital cities and walking out and saying hi. And, if they want to make contact, make contact, right? It seems strange to me that they will be here and sort of doing this weird sort of stuff, but I wouldn't rule it out. I think the problem is, right, again, another Carl Sagan quote, extraordinary claims require extraordinary evidence. So you're really going to need something that is kind of ironclad. And there's a quote from, I think, from Neil deGrasse Tyson, where he says, well, then where are, if these spacecraft are crashing, all over the place, show me, the gear shifter, or show me the landing gear from one of these spacecraft, bring that out and let's take a look at it. Let's examine it. And the thing with SETI experiments, right, is that we're taking a scientific approach. We're sort of agnostic going in, as you should be as a good scientist with any sort of, unproven phenomenon. You go in, you set up an experiment, and the nice thing that we can do with Breakthrough Listen is we understand the instrument, right? It's not some shaky video taken under unknown circumstances of somebody, in a field in Iowa, sort of seeing some bright light, which maybe later turns out to be Jupiter, or, an airplane or something, a weather balloon, I don't know. So we can set up an experiment that actually is under our control and has the capability to take data that we understand, and we can search through that for kinds of signals that could be potentially unambiguously evidence that something interesting is going on. And so we're pretty skeptical. I think we're pretty sort of sober people. None of us are wearing, tinfoil hats and sort of, getting on kind of message boards in the dark corners of the internet, kind of chatting about conspiracy theories. We just want to know, can we do a science experiment in the same way as, nobody knew if there were planets beyond the solar system in the 1980s. And then we did some experiments with some new instruments and we found them. So can we do the same thing with ET? So yeah, I don't know about the flying saucers is the short answer.
We have 3 more questions, if that's okay. So according to what I mentioned before, your interest is reached to black holes too, right? Could JWST in combination with Earth telescopes be used as large array like EHT project to obtain even sharper images of black holes than EHT?
Yeah, good question. I think, I haven't done, I did a lot of work sort of earlier in my career on black holes and their environments. I haven't done so much in that area of late, but I can answer this question. So the EHT, for folks that are not familiar, I mean, really that's sort of a radio astronomy experiment, actually. And you saw that big single dish, the Green Bank Telescope, right? It's a 100-meter dish. And the resolution of that telescope, so the details that it can spot, and this is the detail, you know, this is the question here in terms of imaging a black hole, right? How fine a detail do you need to be able to spot a black hole? Well, the Green Bank Telescope can see, if sort of to put this in scale, right? It's a few arc minutes, depends on the frequency that you look at. So an arc minute is 1/60th of a degree, and so it's about excuse me, about a quarter of a full moon on the sky, basically, something like that is what the Green Bank Telescope sees, and it actually just sees a single pixel. So the Green Bank Telescope is not a camera; it's just basically, if you imagine you're looking at the picture of me here on your screen, imagine instead of seeing detail, you were just seeing the brightness of this. I was just one pixel that was getting kind of brighter and fainter as I'm sort of moving my hands in and out of the frame. And that's about the same size as that picture that I showed of the Hubble Ultra Deep Field. It's about the same region of the sky, but Hubble has much sharper resolution and can see much finer detail within that image. And that's because it's using a wavelength of light that is much, much shorter. It's using optical light or near infrared light. And so you need a much smaller instrument, right? The Hubble Space Telescope is 2.4 meters across. The Green Bank Telescope is 100 meters across. But Green Bank has worse resolution than Hubble because it's a radio telescope, not an optical telescope. So how do you get around this? Well, EHT basically built a telescope that was the size of the planet. How can you do that? How can you build a planet-sized telescope? Well, you can't build a big mirror that's thousands of kilometers across, but you can join up multiple telescopes and join up the signals from them. And if you've seen, you know, this is done more with radio telescopes, the Very Large Array, the telescope in contact, Jodie Foster with the headphones, right? 27 dishes that can be moved around, and they can move the telescopes actually on railroad tracks till at some point they're 36 kilometers apart, and you combine them together. Now you've got better resolution. You got the resolution equivalent to a dish that's 36 kilometers wide. You don't have the collecting area, you don't have the sensitivity, you haven't actually built a big dish that can see really faint things, but it can see very small things. And so if you move those telescopes further and further apart, you put them at, you know, opposite sides of the planet, and you sort of fill in with a few other kind of pairs of telescopes, you can get details that are small enough that you can resolve the detail of the area around the event horizon, hence the Event Horizon Telescope around these supermassive black holes. So, okay, great. So far, so good, right? We're doing this at radio wavelengths, actually at high frequencies, at radio frequencies of sort of 100 gigahertz or so, rather than down where we are at a couple of gigahertz with Breakthrough Listen. Can you do that with JWST? Well, it would be great if you could. You could get even more detail, right? JWST is an optical telescope. Could we combine the information from two optical telescopes to get even better resolution and combine optical telescopes together? It turns out, I probably don't have time to get into why this is the case, but that's much harder to do with optical telescopes. Basically now, because you're dealing with shorter wavelengths, actually, because you have to line up the light. Imagine sort of lining up a radio wave where the radio waves are kind of meters in length, and lining those up is a lot easier than getting something that is, you know, a few hundred nanometers and getting the precision pointing, and especially for something like JWST in space, getting the positions right and stable enough that you could do this kind of interferometry, this is the technique that's used, is not really going to help right now. So we're not going to get, unfortunately, for Mateus, we're not going to get the resolution from that just yet to do better than what we can do on the ground with EHT.
Thank you.
Yeah.
So we have Danielle's question. Is there an initiative to do SETI from other celestial bodies? If so, what are the opportunities to consider? And I would like to ask something related to the question. How about using ALMA's radio frequencies, for example, in Atacama?
Yeah, no, ALMA is a good suggestion. We have sort of had some ideas about using ALMA. The problem is with ALMA that it's in very high demand. And if you go and ask them, can we have 20% of the time on ALMA, they're going to laugh at you. I mean, maybe if you bring them a big check, then maybe, but even so, maybe not. So what we're doing actually with Meerkat, and this is the telescope in South Africa, it's similar to ALMA, but at lower frequencies. We're building a dedicated SETI backend for Meerkat, where we can observe at the same time as other people. And so they say, oh, I'm going to look at this pulsar, or I'm going to look at this quasar or this galaxy. And we say, well, we'll just borrow a bit of your data while you're doing that. You won't notice. We'll just make a copy of it, and we'll analyze that. And we can do that with Meerkat. I think engineering-wise, it will be harder to do that with ALMA. Maybe something that we could look into. We would love to see SETI experiments on many, many telescopes, but no, we're not there with ALMA just yet. But I guess in terms of on other bodies, I mean, this is a good suggestion. Particularly, people have suggested that we could do it on the far side of the moon. Reasons for wanting to do that are there are no cell phones on the far side of the moon. There's no Wi-Fi. There's no Bluetooth. No GPS satellites. There's a couple of things that are in orbit. There's some satellites that are up there. For me, I think part of the problem is going to be that by the time we have the sort of capabilities to do that there will be Wi-Fi and Bluetooth, and there'll be astronauts on cell phones, and we'll already have kind of a radio interference problem on the far side of the moon at that stage, because it will be more developed. Could we do it now? Well, maybe. Think back to that picture of the Green Bank telescope. There's no way you can launch the Green Bank telescope to the far side of the moon, right? 7,000 tons, bigger than the Statue of Liberty. You're not going to put that on a rocket anytime soon. You could maybe do something where you build a much simpler telescope, particularly one that operates at low frequencies, maybe just out of kind of spools of wire that you uncoil out there. People have suggested doing this. It's still a super expensive mission to do, way beyond the $100 million budget that Breakthrough Listen has. So I hope so. I hope so one day, but not just yet.
Great. I mean, there are so much questions in here, but I think, I don't know if you want to answer. We also have a raffle from 2 ebooks that we will raffle from all the participants here. It's Bruce's and Ana Luisa's book. It's really, really good. Everyone should read it. It's about Costa Ricans that have gone to NASA. And even if you are not, or probably, I don't want to be an astronaut, I don't want to work in NASA. I don't know, you might end working as a mathematician or as a doctor or something, and it's really inspiring. So I think it's something we should all read as Costa Ricans and from other countries too.
That's very kind, Andrea, and it's a good point to mention all the different jobs related to the space industry and industries. And Adolfo, in his presentation earlier, mentioned about how we're going to try to bring those jobs home or do them remotely and work in different ways. So, Steve, that was an amazing presentation. Thank you. And really, really amazed. And I hope everyone enjoyed it.
We enjoyed it so much. So let's see who won the raffle of today.
Thank you, Andrea. We have the 2 winners here, and the names are coming up. And first winner up is Genesis Rodriguez Herrera.
Genesis Rodriguez, I see her here. She's there. Hi, Genesis. You just won one of the ebooks.
And here comes the second name, which is Kevin Monge. Congratulations.
Kevin, are you there? You're the happy winner of a book. Genesis, can you write me your email, and Kevin also, so I can send you your codes, or Bruce can send you your codes so you can access your books? I will send you my email, okay?
And thanks very much to the Editorial Tecnológico de Costa Rica for our publisher. That's the Costa Rica Institute of Technology Press, University Press, for giving those books away. And it's wonderful to work with you guys. Thanks again.
And I want to thank both of our speakers tonight. You were really inspiring and it was amazing. I do believe in aliens, so I'm excited. I feel like every time I'm here, I feel like a little girl again. So Bruce there has the his alien. So it was amazing. Thanks so much for being here, for your inspiration, for speaking to us about your job and taking the time.
Thank you for the opportunity. Thanks for the great questions. It was my pleasure, and wish you all the best.
Thanks, Adolfo, and thanks, Steve. It was great to meet you, and I hope everyone took away a lot. And if there's a lesson that we can learn about trying to apply for any internship is, I guess, do your homework. And when you do apply, make sure that you have a really good resume and experience and meet people and learn. So thanks very much for that advice, Steve. Because I know you're very open, but with resources, being limited in that area. But your advice was really, really good. Thanks so much.
Right.
Keep searching.
Thank you very much to all, and good night.
Okay, thanks.
Good night.
All right, thank you.
Everybody's clapping with their hands, virtual hands.